All right, let's dive into this paper everyone's talking about, this one on runaway electrons.
Yeah, it's got some really interesting findings about how they form, especially in the early stages of a fusion plasma.
Right, when it's still weakly ionized.
Exactly. Seems those inelastic collisions, the ones we usually think of as slowing things down, they might actually be helping to create runaways.
Okay, so runaway electrons, they're a big problem in fusion research, we know that.
Huge problem.
But why are they so common in those first moments of plasma formation? What's happening there?
Well, think about it. At the very beginning of a tokamak discharge, the plasma is nowhere near fully ionized. You've got a mix of free electrons zipping around and a bunch of neutral atoms just hanging out.
So it's not your typical plasma environment.
Not at all. And it's this mix that creates a unique situation where those inelastic collisions, the ones that involve energy loss, they can actually contribute to runaway electron generation.
Hold on, how does losing energy make an electron go faster? That seems counterintuitive.
It does, right. You'd think collisions would slow things down, and they do, in a fully ionized plasma. The collisions there are mostly between charged particles, and those are pretty good at sapping energy from speeding electrons.
Right, classic collisions.
But when you throw in a bunch of neutral atoms, the collisions between electrons and those atoms, they behave differently. They're not as effective at slowing the electrons down, especially the ones with lower energies.
So those lower energy electrons, they're getting a free pass, accelerating almost without any resistance.
Until they hit a certain energy threshold, yeah. And once they reach that higher energy, they can cross that critical momentum boundary and become runaways.
It's like they're slipping through the cracks before the plasma is fully formed.
Exactly.
And this is where this paper's deep dive into the Fokker-Planck-Boltzmann, the FPB operator, comes in, right?
Right, because the traditional Fokker-Planck operator, it works great for fully ionized plasmas, where the collisions are mostly those small changes in momentum.
Yeah, charged particle interactions, the standard stuff.
But when you have a lot of electron-atom collisions, you need a tool that can handle those big, dramatic changes in momentum, too.
The ones that can send an electron careening off in a totally different direction.
That's where the Boltzmann part of the FPB operator comes in. It can handle both the subtle nudges and the big hits.
So it's like a more versatile tool, a Swiss Army knife for collision modeling.
Exactly. It lets us see the full picture of electron dynamics, and that's where these surprising results are coming from.
Okay, so we've got the FPB operator taking center stage, and then the paper introduces this parameter H, the soft-hard separation factor. What exactly is H doing here?
Think of H as the dividing line between those soft, grazing collisions that Fokker-Planck handles and the more dramatic, head-on collisions that are Boltzmann's territory.
So it's like setting a sensitivity level.
Sort of.
Yeah.
By adjusting the H value, the researchers can fine-tune the model to see how different mixes of those collision types affect the plasma.
So if you lower H, you're saying, okay, let's consider more of those hard collisions with neutral atoms, right?
Exactly. And what they found is that as you lower H, you see a significant increase in the number of high-energy electrons in the plasma. It's like those hard collisions, instead of slowing things down, they're actually giving some electrons a boost up to that runaway threshold.
That's a wild finding. So it's almost like those hard collisions are making the plasma more chaotic.
In a way, yeah. It's definitely shaking things up.
Okay, so how do they actually show this in the paper?
They use a combination of simulations and visualizations, and one of the key figures, figure 1, it really shows those differences between collision models.
This is what's figure 1 showing us.
It shows something called the deflection frequency, which is basically how often an electron changes direction because of collisions.
Makes sense.
Now, the traditional Thomas Fermi model, which is often used for electron-atom collisions, it predicts a certain deflection frequency. But when they use the FPB model and lower that H value, meaning more hard collisions, that deflection frequency changes dramatically. It really highlights how much those hard collisions are affecting the electron's paths.
Wow, so figure 1 is like a visual representation of those hard collisions, making the plasma more chaotic. It's like adding a bunch of bumper cars into the mix.
Yeah, a good way to put it. And all that chaotic motion, it has a big impact on the overall energy distribution of the electrons, which is what they show in figure 2.
Okay, so figure 2, this is showing the steady state electron energy distribution for different values of H. What are the key takeaways here?
The big thing is that as you lower H, bringing in more of those hard collisions, the tail of the energy distribution, where those really high energy electrons are, it gets much bigger. You see way more electrons with energies high enough to reach that runaway threshold.
So figure 2 is really driving home the point that those hard collisions, the ones we thought were slowing things down, They're actually helping create more runaway electrons.
Exactly. And it really shows why it's so important to use a model like the FPB operator that can handle all those different types of collisions, especially in those early stages of plasma formation where the ionization fraction is low.
And I'm guessing that low ionization fraction is a key factor here, right?
Absolutely. The lower the ionization fraction, the more likely you are to get runaway electrons. And that's especially true when you take those hard collisions into account.
So this has huge implications for ITER and other big fusion reactors.
It does. If we want to control runaway electrons, we need to understand this process thoroughly, especially those early moments when the plasma is first forming.
So how does the paper connect these findings to something like ITER? Do they try to apply these models to a real-world scenario?
They do. They actually used their FPB model to simulate an ITER startup.
Wow, so they're putting these ideas to the test.
Yeah, and the results are pretty eye-opening, especially when you compare them to the predictions of the traditional Fokker-Planck model.
Okay, let's talk about those ITER simulations. What do they show about the impact of those hard collisions on runaway electron generation in ITER?
Well, they've got a whole figure 4, that shows how different parameters evolve over time during that simulated startup. One of the most striking things is the difference in the runaway electron current predicted by the FPB model versus the traditional Fokker-Planck model.
Okay, so figure 4 is showing us the runaway electron current, and it's different depending on which model you use.
Right. Figure 4a, it specifically shows the runaway electron current over time. They label it IRE. The FPB model, which is the solid blue curve in the figure, it predicts a much higher runaway electron current compared to the traditional Fokker-Planck model, which is the dashed red line.
So if you were just looking at the traditional model, you might think you have the runaway electrons under control, but the actual current can be much higher.
That's the worry.
And the paper's saying this could have serious consequences, right?
Definitely. They even ran a simulation with a slightly higher electric field. And the runaway electron current, it completely took over the plasma current, essentially causing a disruption.
So it's like a runaway chain reaction.
Basically. It really emphasizes why we need to use these more accurate models, like the FPB model, to predict runaway electron behavior, especially in those early stages of the discharge.
Okay, before we get into the implications of all this, let's talk a bit more about how they actually set up these ITER simulations. What were their starting conditions?
Well, they chose their initial conditions to reflect a specific point in the ITER startup process. They started the simulation right when closed flux surfaces have formed in the tokamak.
Hold on, closed flux surfaces, remind me what those are again.
Sure. Imagine the magnetic field lines in a tokamak. Ideally, they form these closed loops within the donut-shaped chamber.
Okay, I'm picturing it.
Those loops are the closed flux surfaces. They act like a magnetic cage, keeping the plasma contained and preventing it from hitting the reactor walls.
Right, like a magnetic bottle holding the hot plasma.
Exactly. Now, during the very early stages of plasma formation, those closed flux surfaces aren't fully formed yet. It's more chaotic, with stray magnetic fields all over the place. The researchers chose to start their simulation after those closed flux surfaces have formed because that's when runaway electron confinement becomes really important.
So before those surfaces form, any runaway electrons just get lost to the walls.
Pretty much, yeah. They might be generated, but they don't stick around long enough to build up a significant current.
So they're starting the simulation at a point where the runaway electrons can actually make a difference.
Right.
And that makes sense why they chose an initial ionization fraction of 8%. At that point, the plasma is still weakly ionized, so you have the conditions for those hard collisions.
Exactly. It's that sweet spot where the closed flux surfaces are in place, but the plasma is still weakly ionized, and that's where those differences between the FPB model and the traditional model really show up.
It's all about timing.
It is. And what they found is that the FPB model, because it accounts for those hard collisions, it predicts a much higher runaway electron current, which could be a real problem during those early moments of operation.
This is a lot to take in, but it's incredibly important stuff. So what's next? Where do we go from here?
Well, I think the next step is to really dig into the details of those ITER simulations. Look at how things like runaway electron density and electric field strength change over time.
I'm ready for it.
All right, let's dive back into figure 4.
Let's do it.
This figure is basically a time series showing how all these different parameters change during that simulated ITER startup. Now, the black curves in the figure, those are the output from a fluid code called Dion.
d-on.
Right, and that code's setting the stage for the runaway electrons. It's defining the environment where all the action happens.
Okay, so d-on is like the backdrop for the runaway electron show.
Exactly. Now, if you look at figure 4b, you can see how the electron density, they label it Na, and the neutral hydrogen density, labeled Nh, those are changing over time. You see how the electron density starts low but rises really quickly.
Yeah, it looks like it's shooting up.
That's because during the startup, you're injecting gas and then ionizing it, so the number of free electrons in the plasma keeps going up.
Makes sense. And I'm guessing that rising electron density, that's going to affect the runaway electrons.
It's huge. As the electron density goes up, the collisions between electrons and ions, those become way more frequent, and those collisions are much better at slowing down runaway electrons compared to collisions with neutral atoms.
Right, because those ions are much heavier targets.
Exactly. You can actually see this effect in figure 4c, which shows the runaway electron density labeled NRE. Notice how it spikes early on when the ionization fraction is low, but then it kind of levels off as the electron density increases.
So it's like those runaway electrons have this early window of opportunity, but as the plasma gets more ionized, that window closes.
Exactly. And this is where the importance of those hard collisions really comes into play. Even though the electric field strength, which is shown in figure 4e and labeled E, even though that's relatively low in the simulation, you still get a lot of runaway electrons early on because those hard collisions with neutral atoms are helping to accelerate them.
It's crazy how these tiny collisions can make such a big difference.
It is. But let's go back to figure 4a for a sec, the one with the runaway electron current, IRE. We talked about how it's much higher in the FPB simulation compared to the FP simulation, but how does that actually change over time? What's causing those changes?
Good question.
It's really a combination of things, but the biggest factor is the interplay between the electric field strength and the rate at which those runaway electrons are being generated.
Okay, so we have the electric field pushing them faster, but then the generation rate is also changing.
Right. Early on, when the ionization fraction is low, the runaway electron generation rate is high, even though the electric field is still low. That's because those hard collisions are giving those electrons a boost. But then as the electron density increases and the ionization fraction goes up, the generation rate starts to decrease, even though the electric field is getting stronger.
So it's like a tug of war.
Exactly. And the balance between those two forces determines what happens to the runaway electron current. In the FPB simulation, which is the one that accurately models those hard collisions, the runaway electron current gets much higher than in the FP simulation.
So this is why it's so important to use the right model, the one that captures the full picture.
Absolutely. If you're relying on those older models, you might be underestimating the risk of runaway electrons, especially in those early moments of the discharge.
And that could have serious consequences for the reactor.
Exactly. This research is really a wake-up call. It's telling us we need to pay close attention to those early moments and use the most accurate models we have to predict and control runaway electron generation.
This has been incredibly insightful, but I feel like we've only just scratched the surface. There's so much more to unpack here.
Definitely. We've laid the groundwork, but there's a lot more to explore, especially when it comes to the implications for ITER and other fusion reactors.
And what about controlling these runaway electrons? Are there strategies for that?
Oh, absolutely. There are a lot of different approaches being developed, both for preventing runaway electrons from forming in the first place and for mitigating them once they've appeared.
Okay, so we've got prevention and mitigation.
Right. We can get into the details of those strategies in the next part of our deep dive.
Sounds good. I'm ready when you are.
All right, let's dive in. Welcome back, everyone. Let's pick up where we left off runaway electrons and how we can control them.
We were just talking about all these strategies for dealing with runaway electrons, both preventing them and mitigating the damage once they've formed.
Yeah, there's a whole toolbox of techniques being developed.
Okay, so let's open that toolbox. What are some of the ways researchers are trying to prevent these runaway electrons from forming in the first place?
Well, one common approach is to very carefully control the electric field during that initial plasma startup phase.
Right, because the electric field is what's accelerating those electrons in the first place.
Exactly. If you can keep the electric field below a certain threshold, you can reduce the chances of those electrons reaching the energy they need to become runaways.
Makes sense. But I'm guessing it's not always that easy. You need the electric field to heat the plasma, right?
Absolutely. You can't just turn it off completely. It's a delicate balancing act. You need enough electric field to drive the plasma current and get the plasma hot enough, but not so much that you're creating a runaway electron factory.
So it's like finding the Goldilocks zone for the electric field. Not too hot, not too cold.
Perfect analogy.
Okay, so that's prevention. What about mitigation? What are some of the strategies for dealing with runaway electrons once they've already formed?
Well, one promising technique is injecting impurities into the plasma.
Impurities. How does that help?
It's all about increasing the collisionality of the plasma. Those impurities, they bump into the runaway electrons, making it harder for them to maintain their high energies.
So it's like throwing a bunch of obstacles in their path.
Exactly. Those impurities act like speed bumps, slowing those electrons down before they can cause too much trouble.
I like that speed bumps for runaway electrons. Are there any other mitigation strategies in the works?
Oh yeah, lots of cool ideas out there. Another interesting one is using magnetic perturbations to disrupt the runaway electron beam.
Magnetic perturbations. What are those?
Basically, they're small, deliberate ripples in the magnetic field. They can scatter those runaway electrons, reducing their energy and making them less of a threat.
So you're messing with the magnetic field to throw those runaway electrons off course.
Exactly. It's like throwing a wrench into the gears of that runaway electron beam.
I'm sensing a theme here. Lots of analogies involving disrupting the runaway electron's smooth ride.
It's a good way to think about it. We're trying to make their lives as difficult as possible, keep them from causing trouble.
Makes sense. Now, how does this new research on inelastic collisions change things? Does it affect our approach to controlling these runaway electrons?
It definitely adds a new layer of complexity. It really highlights how important those early moments of tokamak operation are, when the plasma is still weakly ionized and those hard collisions are happening all the time.
Because even with a low electric field, you can still get a lot of runaway electrons forming.
Right. The traditional models might not capture that, so they could be giving us a false sense of security.
So we need to be extra careful during those early moments.
Exactly. This research is telling us we need to use models like the FPB model, the one that can accurately account for those hard collisions, to predict runaway electron behavior throughout the entire discharge.
So practically speaking, how does this change our strategies for controlling runaway electrons?
Well, for prevention, it means we might need to be even more careful with that electric field during those early stages. Even small increases could lead to way more runaway electrons than we expect, especially when the plasma is weakly ionized.
So we need to be really precise with that electric field control.
Exactly. And for mitigation, it suggests that we might need to deploy those strategies earlier in the discharge before the runaway electrons really get going.
So like a preemptive strike to stop them before they can build up momentum?
Exactly.
This all points to a much more dynamic approach to runaway electron control.
It does. We need to adapt our strategies based on the specific conditions of the plasma at each stage of the discharge.
Okay, before we move on, I want to go back to something you mentioned earlier about using impurities to slow down those runaway electrons. What kinds of impurities are we talking about, and how do you actually get them into the plasma?
Great question. The specific impurities you use depend on a bunch of factors, like the tokamak design and the plasma parameters. But some common ones are noble gases like argon or neon. Sometimes even heavier elements like nitrogen or krypton are used.
So you're basically choosing the right type of speed bump for the job.
Yeah, exactly. And how you get those impurities into the plasma, that can vary too. One way is to inject puffs of gas directly into the chamber. Another is to use pellets of frozen impurity material that you shoot into the plasma.
Frozen pellets. Sounds high-tech.
It is, and there's a whole lot of engineering that goes into making sure those impurities get where they need to be and in the right amounts.
Because too much of a good thing could actually hurt the plasma, right?
Absolutely. You don't want to overdo it. It's all about finding that sweet spot.
Okay, I think I'm getting a much better grasp on the practicalities of runaway electron control. But now I'm curious about the math behind all this. Can we dive a little deeper into that FTB operator? How does it actually work?
Sure. Remember, the FPB operator combines two different approaches to describing collisions: the Fokker-Planck operator and the Boltzmann operator.
Right. The Fokker-Planck operator is good at handling those small, gentle collisions, and the Boltzmann operator takes care of the big, dramatic ones.
Exactly. Think of the Fokker-Planck operator as describing those tiny nudges that a particle experiences from its neighbors, causing it to gradually change its velocity. It's like a smooth, continuous process.
Okay, that makes sense for those small nudges. But how does the Boltzmann operator handle those big hits?
The Boltzmann operator doesn't assume those small changes in momentum. It accounts for those big, sudden collisions that can send a particle off in a completely different direction.
So it's like the difference between a gentle breeze and a sudden gust of wind.
Yeah, that's a good analogy. And the FPB operator is able to combine both of those descriptions into one mathematical framework.
So it can handle the full spectrum of collisions, from those tiny nudges to those big game-changing hits.
Precisely. And it does it in a way that avoids double counting those collisions, which is really important for accuracy.
Hold on, double counting, what does that mean?
Well, imagine you have a collision that causes a big change in energy. That collision could potentially be categorized as both a hard collision by the Boltzmann operator and a soft collision by the Fokker-Planck operator.
So it's like counting the same thing twice.
Exactly. And if you do that in your model, it can skew the results.
So how did the FPB operator avoid that?
It carefully defines the boundaries for something called the Coulomb logarithm in the Fokker-Planck part of the equation. The Coulomb logarithm is basically a way to represent the cumulative effect of lots of small-angle collisions.
Okay, but how does adjusting that prevent the double counting?
By setting those boundaries, the FPB operator makes sure that any collision that's already been handled by the Boltzmann operator isn't included in the Fokker-Planck calculations. It's like sorting your laundry into different piles. You don't want to wash your delicates with your heavy-duty clothes.
Keeps everything nice and organized.
Yeah. Exactly, and that's really important for the accuracy of the FPB model. It's able to account for both the soft and hard collisions without any double counting, which gives us a much more realistic picture of what's happening in the plasma, especially in those early stages when those hard collisions are so important.
This has been a really deep dive into the math, and it's fascinating stuff. But I think it's time to zoom out a bit and think about the bigger picture. What are the implications of all this for the future of fusion energy?
Absolutely. Let's shift gears and talk about what this all means for our quest to harness the power of the stars. All right, welcome back to our discussion on runaway electrons.
We've been digging into the nitty-gritty of these particles, how they form, those surprising hard collisions, and all the strategies for keeping them under control.
And now it's time to step back and think about the big picture. What does this all mean for fusion energy, especially for projects like ITER?
Right, ITER, the giant fusion experiment everyone's watching. Runaway electrons are a big challenge for ITER, aren't they?
They are. It's one of the major hurdles we need to overcome if we want ITER to succeed and pave the way for fusion power.
So this new research on inelastic collisions, it's really important for ITER, isn't it?
It is. It tells us we need to be even more careful about runaway electrons, especially in those early moments of the plasma discharge when the ionization fraction is low and those hard collisions are so common.
Because even if the electric field seems low, you can still get a lot of runaway electrons forming.
Exactly. We need to think about runaway electron mitigation throughout the whole process, right from the start.
So it's a more holistic approach.
Exactly. And it involves thinking about things like pre-ionization strategies, how we heat the plasma, and even the design of the magnetic confinement system.
Okay, let's break those down one by one. Starting with pre-ionization. Why is that so important when it comes to runaway electrons?
Well, pre-ionization is all about creating a small population of free electrons in the fusion fuel before the main heating even starts. It's like setting the stage for the plasma to form.
So you're giving the plasma a head start.
Exactly. And those initial electrons, they help to ionize the rest of the fuel, which can really reduce the chances of runaway electrons forming in those early moments.
Because as the ionization fraction goes up, you get more of those collisions between electrons and ions, which are better at slowing down the runaways.
Exactly. It's like we're racing against the clock to get the plasma fully ionized before those runaway electrons can really take off.
So the choice of pre-ionization technique, that could make a big difference.
It could. Different techniques have different efficiencies and create different patterns of ionization, and those can affect both the runaway electron generation rate and how well they're confined.
So it's another one of those balancing acts we need to figure out.
It is. We need to choose a pre-ionization method that can quickly and effectively ionize the fuel, creating a plasma environment that's less favorable for runaway electrons.
Okay, that's pre-ionization. What about plasma heating? How does that play into the runaway electron problem?
Well, the heating method you use, it determines the overall temperature and energy distribution of the electrons in the plasma. And that energy distribution, that's what dictates how many runaway electrons you're likely to get.
Because it's those high-energy electrons in the tail of the distribution that are most likely to become runaways.
Exactly. They have enough energy to overcome the friction from collisions and just keep accelerating.
So different heating methods can have different effects on the runaway electron population?
They can. Some methods might be more prone to creating those high-energy electrons that are likely to become runaways.
Can you give me an example?
Sure. Ohmic heating, which uses the resistance of the plasma itself to generate heat, that tends to create more high-energy electrons compared to other methods like radio frequency heating or neutral beam injection.
So ohmic heating might be a bit riskier when it comes to runaway electrons.
It can be, especially early on when those hard collisions are also contributing to the problem. But there are ways to mitigate that risk, like carefully controlling the electric field or using a combination of heating methods.
So we need to choose our heating method wisely.
Absolutely. It's all about finding the right balance between heating the plasma effectively and minimizing the risk of runaway electrons.
Okay, we've talked about pre-ionization and heating. What about the overall design of the magnetic confinement system? How does that affect runaway electrons?
The magnetic confinement system, that's what keeps the plasma contained, right? Those closed flux surfaces we talked about, those magnetic cages, they're essential for preventing runaway electrons from hitting the reactor walls and causing damage.
Right, those magnetic field lines act like walls, keeping everything in place.
Exactly. But even small imperfections in the magnetic field can create pathways for those runaway electrons to escape.
So it's like having a leak in your container.
Yeah, kind of. We need to make sure that magnetic field is as strong and stable as possible to keep those runaway electrons contained.
This all just shows how complex fusion energy research is. There are so many interconnected factors to consider.
It's true. It's a multidisciplinary challenge, and we need experts from all different fields working together to solve it.
Well, I think we've covered a lot of ground in this deep dive. We've gone from the fundamental physics of runaway electrons all the way to the implications for fusion reactor design and operation.
It's been a fascinating journey.
It has, and it's clear that this new research on inelastic collisions, it's really changing the game. It's forcing us to rethink our strategies for dealing with runaway electrons.
It is. We need to be more careful, more precise, and more proactive in our approach.
And that's the only way we'll be able to harness the power of fusion safely and efficiently.
Absolutely. It's a challenge, but it's one that's worth taking on. After all, we're talking about potentially unlocking a clean and sustainable energy source for the future.
That's a goal worth striving for.
It is.
Well, on that note, I think it's time to wrap up our deep dive. Thanks for joining us on this exploration of the fascinating world of runaway electrons. Until next time, keep those brains buzzing and stay curious. All right, let's dive deep today. We're looking at runaway electrons in tokamaks. You've given us a really interesting research paper to work with. Inelastic collisions, facilitating runaway electron generation in weakly ionized plasmas. I bet you're really curious about how these inelastic collisions make this runaway electron problem even worse, especially during that startup phase of tokamaks. We're going to unpack all that, looking at the complex interactions of electron collisions, those electric fields, and plasma ionization levels.
Yeah, it's a super important area, especially as we get closer to larger tokamaks like ITER.
For sure. But first, just to get us all on the same page, what exactly are these runaway electrons? Are they like tiny little speed demons inside the tokamak? What makes them such a big deal?
You can think of a tokamak like a really precise ballet.
Yeah.
You've got this superheated plasma swirling around gracefully inside the magnetic field lines. But runaway electrons, well, they're the rebels in the performance. They pick up so much energy that the magnetic fields can't hold them anymore. And then, boom, they slam right into the tokamak walls. That can cause damage, make things unstable, and even interrupt the whole fusion reaction.
Oh, wow. That sounds like a disaster waiting to happen,
Yeah.
especially with ITER being so huge. So how do these electrons become runaways in the first place? What gives them that push towards, chaos?
Well, there are a couple of ways they get that runaway energy, but this paper focuses on something called the Dreiser mechanism. It happens especially during startup when the plasma is just forming. Basically, there's this electric field trying to drive a current through the plasma. Electrons are always bumping into other particles, which usually acts like a brake, slowing them down. But sometimes, if the electric field is strong enough, some electrons can actually break free from that drag force and accelerate like crazy.
So like they're hitting the gas while everyone else is stuck at a red light.
Exactly. And there's this critical threshold, like a speed limit, that an electron has to pass to become a runaway. We call it the critical momentum, written as P sub c.
Gotcha. So P sub c is the point of no return. Once they hit that speed, they're off to the races.
Right. Now, in a fully ionized plasma, where you mostly have electrons and ions, we can model this runaway process pretty accurately using something called the Fokker-Planck equation. It's a mathematical model that tracks how the distribution of electron velocities changes over time.
So it's like our roadmap for understanding these runaways in a nice, clean plasma. But this paper focuses on weakly ionized plasmas, right? So what happens when we introduce neutral atoms into the mix?
Ah, that's where things get really interesting. And it's where the Fokker-Planck approach starts to break down. Because when you have neutral atoms, those electron-atom collisions become way more important. And they're not always the gentle bumps that the Fokker-Planck equation assumes.
Oh, so the neutral atoms are like adding obstacles to the racetrack.
That's
It
right.
changes the game for our runaway electrons.
You got it. The real trouble starts when the energy of an electron is about the same as the ionization potential of the atom. That's the energy you need to knock another electron off the atom and make an ion. At that energy level, the collisions can be a lot more violent. They can cause big changes in the electron's direction and energy. The small angle collision assumption that the Fokker-Planck model relies on just doesn't work anymore.
So our trusty Fokker-Planck equation hits a wall when we have these more chaotic collisions. Does that mean we need a whole new model to understand runaway electrons in these weakly ionized plasmas?
Well, not completely. This paper proposes a really elegant solution. It's called the Fokker-Planck-Boltzmann, or FPB, operator. This approach lets us account for both the soft collisions, the ones that the Fokker-Planck equation handles well, and the hard collisions, those large angle ones that become important in weakly ionized plasmas.
So it's like a hybrid model, combining the best of both worlds.
Yeah.
How does it actually work? How does it tell the difference between soft and hard collisions?
It's pretty smart, actually. The FPB operator uses something called H, which represents the fraction of energy lost in a collision. If a collision has an energy loss fraction greater than H, we call it hard, and handle it with the Boltzmann operator. That operator is better at handling those more dramatic collisions. Collisions with a loss fraction below H, those are soft, and we use the familiar Fokker-Planck operator.
So it's like having two specialized mechanics working on a race car. One handles the regular tune-ups and the other one is there for those major crashes.
I like that analogy. By combining these two approaches, the FPB operator gives us a much more accurate picture of how electrons behave in these weakly ionized plasmas, especially during that critical startup phase.
Okay, I'm starting to see how this FPB model could be a game changer. Now, the paper says something pretty surprising. It says that those hard collisions, the inelastic ones, actually help generate runaway electrons. That doesn't seem right, does it? Shouldn't collisions be slowing the electrons down?
It's a really interesting finding. What the research shows is that these hard collisions, specifically the ones called non-differential inelastic collisions, can actually give some electrons a boost towards runaway energies.
Hold on. Are you saying some electrons are getting a slingshot effect from these collisions? How does that even work?
Think of it this way. In those hard collisions, the energy transfer isn't always smooth and gradual. Sometimes an electron hits an atom and loses barely any energy at all, like bouncing off a trampoline instead of sinking into a soft cushion.
So some electrons are hitting the gas even harder after a collision, while others are getting bogged down.
Exactly. And because of these lucky bounces, some electrons can reach that critical momentum, that P sub C we talked about, really fast. That pushes them right into the runaway zone.
Wow, that's a crazy twist. We might need to rethink our ideas about collisions. So what happens when we compare the FPB model to the traditional Fokker-Planck model? Does it make a big difference?
The difference is huge, actually. The paper shows this in Figure 2, which shows something called the steady-state electron distribution function. It's basically a snapshot of how many electrons are at each energy level.
Like a population map for electrons showing where they are in terms of energy.
Right. And what we see is that the FPB model shows a lot more electrons at those high energies in the runaway zone compared to the Fokker-Planck model.
So the FPB model is painting a scarier picture, with more electrons ready to go rogue. What does that mean for how fast these runaways are being produced? What about the Dreiser generation rate?
That's a great question. The paper tackles that head-on in Figure 3. This figure shows how the Dreiser generation rate changes based on the plasma's ionization fraction. That's basically the ratio of free electrons to neutral atoms.
Meaning a higher ionization fraction means fewer neutral atoms.
Exactly. And the figure shows that accounting for those non-differential collisions, the hard ones that can slingshot electrons towards runaway energies, leads to a much higher Dreiser generation rate, especially in those weakly ionized plasmas.
So the more neutral atoms we have, the more those lucky bounces come into play and the more runaway electrons we get.
Precisely. But here's another important point. Figure 3 also shows that the effect of these non-differential collisions is a separate factor on top of the electric field's influence.
Meaning that a stronger electric field still means more runaway electrons generally. But those neutral atoms and those hard collisions can make that effect even stronger.
You got it. And that's where things get really interesting when we start thinking about ITER and other big tokamaks in the future, especially because ITER is going to operate with incredibly strong electric fields during startup.
Now you've got me really curious. Let's dig into those implications and see what all this means for the future of fusion research. So we've seen that these non-differential inelastic collisions play a big part in creating runaway electrons, especially during startup when the plasma is still weakly ionized. And we've gone through the math of the Fokker-Planck-Boltzmann operator, which does a great job of describing how both those soft and hard collisions work. But now the big question is, what does all this mean for ITER?
That's where things get real. The paper tackles this question head-on. They ran simulations of a startup scenario like ITER's, comparing the predictions of the usual Fokker-Planck model with the more accurate Fokker-Planck-Boltzmann model. And the results, shown in Figure 4, are pretty eye-opening.
Let's break down Figure 4. What's the story here? What happens when we compare those two models in the context of ITER startup?
The difference is huge. The simulations using the FPB model show way more runaway electrons, both in terms of density and the current they carry, compared to the FP model. In this specific scenario, the runaway current gets up to a whopping 7.5% of the total plasma current.
Wow, 7.5%. That's a big chunk of the current being carried by these rogue electrons. What happens when you have that much runaway current during startup?
Think about it this way. The whole point of the startup phase is to heat the plasma carefully and create a stable, controlled current. But if a bunch of that current is being carried by runaway electrons, it's like trying to conduct an orchestra with a bunch of instruments playing out of tune. It can mess up the heating process, create instabilities, and might even cause the whole plasma to shut down.
It sounds like runaway electrons could really sabotage ITER, especially in those crucial first stages.
Exactly. And the paper points out that it could be even worse than their simulations suggest. They say that even a small increase in the electric field, which is already planned to be pretty strong in ITER, could lead to the runaway current taking over completely. Basically, the runaway electrons could hijack the whole startup process, leaving the plasma dominated by these uncontrollable particles.
That's a scary thought. So we know that these non-differential collisions can really boost runaway electron generation, especially in the weakly ionized plasmas we see during startup. And we've seen how that could be a big problem for ITER success. But is there anything we can do about it? Can we solve this problem, or are we just stuck with these rogue electrons ruining our fusion dreams?
Well, that's the challenge, and researchers are actively working on it. Luckily, understanding the role of these collisions gives us a better starting point for coming up with ways to stop them. It's like knowing your enemy, it helps you come up with a better strategy.
Okay, so we're not completely helpless. We have some options. What are some of the strategies being considered to deal with this runaway electron problem?
One thing we can do is carefully manage how we ramp up the electric field during startup. Instead of flooring it right away, we could try a more gradual increase in the electric field, which would reduce that initial burst of runaway electrons.
So it's like easing into traffic instead of trying to merge at full speed.
Exactly. Another strategy is to introduce impurities into the plasma. These impurities can increase the collision rates, which can help suppress the runaway generation. It's like adding more friction to the system, making it harder for those electrons to accelerate out of control.
Interesting. So we're trying to tweak the plasma's properties to make it less friendly to runaway electrons.
Right. And there are other more innovative approaches being explored too, like using specially designed magnetic fields to try and steer those runaway electrons away from the tokamak walls.
It's like building an obstacle course for those runaway electrons, trying to keep them contained.
That's a good way to put it. It really shows how creative researchers in this field are, constantly pushing the limits to find solutions to these tough challenges.
This paper really dives deep into the math behind the FBB model. It gives us a solid framework for understanding how collisions interact in these weakly ionized plasmas. It's clear that being able to accurately describe those dynamics is crucial for predicting and mitigating runaway electrons. Maybe we could take a closer look at some of the key equations and concepts that form the foundation of this model.
Yeah, I'd be happy to walk through some of the mathematical highlights. One of the most important concepts in the FPB model is the idea of separating collisions into soft and hard categories, depending on how much energy is lost in each collision. This is represented by the parameter h, which acts as a kind of dividing line. Collisions with an energy loss fraction greater than h are treated as hard collisions, while those with the loss fraction below h are considered soft.
So H is like the cutoff point between those gentle nudges and the big hits that can send those electrons flying.
Exactly. Now, the paper goes into a lot of detail about how to calculate the collision frequencies for both soft and hard collisions. For the soft collisions, they use the standard Coulomb collision frequencies, which depend on the plasma's density and temperature.
So we're using well-established formulas for those soft collisions, the ones that the Fokker-Planck equation handles well.
Right. But for those hard collisions, things get more complicated. The paper uses a cross-section-based approach. This approach takes into account the specifics of how electrons and neutral atoms interact.
So we're getting down to the atomic level, considering the quantum mechanics of those collisions.
Exactly. They introduce this important value called the energy loss fraction. It's denoted by X, and it represents how much of the electron's energy is lost in a hard collision. This value is super important for figuring out whether an electron is likely to be accelerated towards runaway energies or slowed down.
So ARC tells us how much oomph an electron loses in a hard collision.
I like that way of putting it. And the paper gives us detailed formulas for calculating acquisition based on the scattering angle and the ionization potential of the neutral atom.
This is getting pretty deep into the physics of collisions, but it's really cool to see how these tiny details can have such a big impact on how the plasma behaves as a whole.
It really shows how interconnected physics is, how even the smallest interactions can affect the entire system.
Absolutely. Now let's zoom back out to the bigger picture. This paper gives us a lot of valuable insights into how collisions contribute to runaway electron generation, but it also raises some interesting questions about the limits of our current models. One thing that jumped out at me was the discussion of Coulomb logarithms. Could you explain what those are and why they might be a problem in this context?
That's a good point. Coulomb logarithms are basically mathematical shortcuts we use to simplify calculations involving charged particle interactions. They help us deal with the fact that we can't really consider the interactions between every single particle in the plasma individually.
So it's like averaging out the effects of all those countless interactions.
Exactly. And for a lot of plasma physics problems, Coulomb logarithms work just fine. But in this case, where we have both soft and hard collisions, and that critical energy range where the hard collisions become dominant, it's not so clear if using Coulomb logarithms is still valid.
So our trusty shortcuts might not be so trustworthy in this more complex scenario.
That's the concern. And the paper acknowledges this limitation, suggesting that we need more research to figure out the right way to handle Coulomb logarithms when using the FPB model.
It's a good reminder that even our most advanced models are still just approximations of reality. There's always room for improvement and refinement.
For sure. And this shows how important it is to constantly question our assumptions and look for ways to improve our models as we learn more about these complex phenomena.
This deep dive has been really insightful. We've covered a lot of ground, from the basics of how runaway electrons are generated to the complex math of the FPB model and the experimental data that supports it. But we're not done yet. In Part 3, we'll look at what these findings mean for the future of fusion research, and we'll explore the exciting possibility of actually using runaway electrons to our advantage. Stay tuned. So we've spent a lot of time talking about how to stop runaway electrons, but what if we could use them to our advantage?
That's an interesting idea, and it's something researchers are actually looking into. One of the most promising areas is in controlling plasma disruptions. Those disruptions are a major headache when it comes to tokamaks.
Yeah, I remember. They happen when the plasma suddenly goes unstable and crashes into the walls.
Exactly. It's like a controlled burn suddenly turning into a wildfire.
Yeah.
And it releases a ton of energy all at once.
That sounds pretty bad.
It is. Disruptions are a big threat to the tokamak itself. But there's some evidence suggesting that we might be able to use runaway electrons to actually make disruptions less damaging.
Wait, so you're saying we could use the very things we've been trying to get rid of to actually protect the tokamak?
Exactly. The idea is that if we could create a controlled burst of runaway electrons during a disruption, it would act like a safety valve. Instead of all that energy hitting a small part of the wall all at once, the runaway electrons would spread the energy out over a wider area.
So it's like diverting a lightning strike with a lightning rod.
That's a good analogy. It's still an active area of research, but early simulations and experiments suggest that it could work.
That's pretty amazing, turning a problem into a solution. But are runaway electrons something we only see in tokamaks? Or do they happen in other kinds of plasmas too?
Good question. Runaway electrons aren't just a fusion thing. We see them in nature and in other technologies that use plasmas. For example, they're thought to be involved in lightning. The strong electric fields and thunderstorms can accelerate electrons to super high speeds.
So those lightning bolts we see could be caused by runaway electrons.
It's possible. And they're also thought to be part of solar flares, those huge bursts of energy from the sun.
Wow, so we're talking about things that are vastly different in size. Tiny lab plasmas and the enormous power of the sun. It's crazy to think that these runaway electrons might connect such different events.
It shows just how fundamental plasma physics is. Some phenomena are universal, no matter the scale. And don't forget those other technologies you mentioned. Runaway electrons are relevant in things like making semiconductors and processing materials. They use plasmas for etching, depositing materials, and modifying surfaces.
So understanding runaway electrons isn't just about fusion energy. It affects all kinds of technologies that we use every day.
Exactly. The more we learn about these particles, the more ways we'll find to use them to our advantage.
This deep dive has been a real eye-opener. We started with a specific issue in fusion research, but we've ended up talking about things like astrophysics, weather, and material science. It just goes to show how connected science is, and how fundamental research can open up so many new possibilities.
I agree. It really emphasizes how important it is to keep exploring and working together across different fields of science. The more we learn about the universe, the more we see how everything fits together.
So to everyone listening, here's something to think about. The next time you see a lightning storm or a picture of a solar flare, remember those tiny runaway electrons zooming around at almost the speed of light. They're part of this incredible cosmic dance. Who knows what other mysteries these particles hold, or what amazing things we'll discover as we continue to explore the world of science.
The future of discovery is bright. I can't wait to see what we find next.
Thanks for joining us on this deep dive. Until next time, keep exploring, keep asking questions, and keep that curiosity alive. All right, so today we're going to be taking a deep dive into a pretty complex topic.
Oh, yeah.
Runaway electrons in weakly ionized plasmas.
Okay.
And you shared some research with me on how inelastic collisions can really kind of shake things up in this area.
Absolutely.
Particularly during tokamak startup.
Yeah, it's a critical time.
It seems like these collisions might be even more significant than we previously thought.
Much more than we thought, yeah.
So this obviously has big implications.
Huge implications.
For large-scale reactors like ITER.
Like ITER, yeah.
And we really can't afford to get this wrong.
No, we can't.
Because if we do, we could end up with a runaway situation.
Literally.
Yeah. Literally.
Yeah.
Your research dives into the Dreiser mechanism, which is a key process for generating these runaway electrons.
Yes.
So can you just remind us how that works?
Sure. The Dreiser mechanism is essentially like this. You have an electric field applied to a plasma.
Okay.
That field accelerates the electrons. Now, normally collisions would keep the electron energies in check.
Okay.
But if an electron gets a big enough kick from the electric field and surpasses a critical momentum threshold, it can essentially break free from the drag force caused by collisions and start accelerating uncontrollably.
So it's like a threshold effect.
Exactly.
Once you cross that threshold, off to the races.
Off to the races, exactly. That's the essence of the Dreiser mechanism.
And the paper you shared with me is called Inelastic Collisions, Facilitating Runaway Electron Generation in Weakly Ionized Plasmas.
Right.
And it focuses on how inelastic collisions can actually enhance this process.
Right.
Especially in those weakly ionized plasmas we see during tokamak startup.
It's really interesting.
I always thought collisions slowed things down.
You would think so.
Not speed them up.
You would think so, but...
So how does that work?
Here's the thing.
Okay.
The traditional models, which often rely on something called the Fokker-Planck operator, assume that all collisions are soft, meaning they result in small, gradual changes in momentum. But in weakly ionized plasmas, you also have these hard, non-differential inelastic collisions.
So what's the difference between a hard and a soft collision?
A soft collision, an electron kind of loses a little bit of energy, changes direction slightly.
Like a gentle nudge.
Like a gentle nudge, yeah.
Okay.
But in a hard collision, an electron can lose a significant amount of energy,
Right.
or even none at all in a single interaction.
Okay.
It's more like a sudden jolt.
Ah, so those hard collisions could actually help an electron maintain its high energy, even though it's collided with something.
Exactly.
Yeah.
And that's where the traditional Fokker-Planck model falls short.
Okay.
It doesn't fully capture the impact of these hard collisions.
Yeah.
And what this paper is saying is
Yeah.
that could lead to a significant underestimation
Okay.
of the runaway electron generation rate.
So let's get into the details then.
Sure.
The paper starts off by, setting the stage,
Right.
describing the context of tokamak startup
Mm-hmm.
and why runaway electrons are such a concern.
Yeah.
It points out that during startup,
Yes.
the plasma is relatively cool and not fully ionized,
Right.
which means there's a mix of
Free electrons,
and neutral atoms
neutral atoms.
bouncing around.
Exactly. All bouncing around.
And this creates a perfect environment
It does.
for those hard inelastic collisions to occur.
Yes.
But it's a bit of a catch-22, right?
It is.
Because we need a strong electric field
Right.
to drive the current and heat up the plasma during startup.
Get it going. Yeah.
But that same electric field
Yeah.
can also accelerate electrons toward runaway energies.
Towards runaway. Exactly.
It's a very delicate balancing act.
It's a very delicate balancing act.
Now, the paper introduces
Yes.
the Fokker-Planck-Boltzmann operator,
The FTB
the FPB operator, yeah,
as a more accurate way to model electron behavior.
and
Exactly.
these weakly ionized plasmas.
It's a much better model.
So how does that work? How is that different?
So the FPB operator is like a hybrid model.
Okay.
It uses the traditional Fokker-Planck part
Okay.
to handle those soft collisions,
Mhm.
but it also incorporates the Boltzmann operator,
Okay.
which is better suited for describing those hard, non-differential collisions.
So it combines the best of both worlds.
It combines the best of both worlds.
Okay. And to distinguish between the soft and hard collisions
Yeah.
within the FPB operator,
Mm-hmm.
they use something called the soft-hard separation factor,
Right.
which is denoted by H.
Little h. Yeah.
So if the energy loss fraction of an electron
Yes.
during a collision is greater than H,
Greater than h.
it's considered a hard collision
Regard. Yep.
and handled by the Boltzmann operator.
Boltzmann. Yep.
Less than H.
If it's less than h.
It's a soft collision,
It's a soft.
and it's dealt with by the Fokker-Planck part.
And that's dealt with by Fokker-Planck.
So H is like a filter,
Yeah, it's like a filter.
separating the collisions based on
Yeah.
their impact
And the energy
on the electron's energy.
of the electron.
Okay, now let's get to the math.
Sure.
The paper presents some equations
Yes.
for things like
Yeah.
slowing down frequency,
Slowing down frequencies. Yep.
deflection frequencies,
Deflection frequency.
and the Boltzmann operators
Boltzmann operators. Yes.
for ionization and excitation.
Right. And these are very important because
Yeah.
they help us understand
Yeah.
how the researchers actually modeled these different collisions
Okay.
and their impact on electron behavior.
So let's start with equation 3.
Okay, so equation 3 describes the slowing down frequency
Yeah.
for those soft free-bound collisions
Mhm.
between electrons and hydrogen atoms.
Okay, can you explain what slowing down frequency means?
Yeah, so imagine an electron is moving through a plasma
Okay.
and it encounters other particles.
Hmm.
It loses energy through collisions, right? Yeah.
The slowing down frequency
Okay.
essentially measures how quickly that electron loses energy
Okay.
on average due to
Alright.
those collisions.
So a higher slowing down frequency means the electron's losing energy more rapidly.
More rapidly, that's right.
Okay.
Now, in this specific case,
Yeah.
equation 3 actually takes into account contributions
Okay.
from both ionization
Yeah.
and excitation processes.
Okay.
So it considers the
Yeah.
cases where an electron knocks another electron
Mm-hmm.
out of a hydrogen atom completely.
Which is ionization.
Ionization, right?
Okay.
And the cases where it just bumps it up
Yeah.
to a higher energy level.
Which is excitation.
excitation.
So it's a combined effect.
It's combined.
Okay.
Yeah.
What about those deflection frequencies in equation 4?
Yeah, so those deflection frequencies,
Yeah.
they describe how much an electron's direction changes
Okay.
due to collisions.
Okay.
And they have separate terms for collisions with bound electrons and with hydrogen atoms.
So essentially, they quantify how much the electron is scattered by these interactions.
Okay, and I remember the paper mentioned something about the Thomas Fermi model having limitations.
Yeah, so the Thomas Fermi model, or TF model for short,
Okay.
is often used to describe the scattering of energetic particles.
Okay.
It gives you an idea of how likely a particle is to be deflected by a certain angle when it collides with another particle.
Okay.
However,
Yeah.
the TF model is not very accurate at low energies.
So not a perfect fit for what we're dealing with here.
Not a perfect fit, no.
Okay.
So the researchers in this paper had to make some adjustments to the model to improve its accuracy.
At those lower energies.
At lower energies, yeah.
Okay.
They used experimental data and information from the NIST standard database to kind of fine-tune the model's parameters.
So they're calibrating it to reflect reality.
Calibrating it, exactly,
Right.
yeah.
And the results of this calibration are shown in Figure 1A.
Right, so in Figure 1A...
You can see how that adjusted scattering frequency calculated using the refined TF model aligns much better with the experimental data.
Much better.
Especially at those lower energies.
Especially at low energies.
And then Figure 1B shows a similar comparison for the slowing down frequency.
For the slowing down frequency.
And the curve there, calculated using the FPB model, deviates from the traditional Bethe model at lower energies.
At lower energies, that's right.
Can you remind us what the Bethe model is?
Yeah, so the Bethe model is another commonly used formula for calculating the energy loss of charged particles. But just like the Fokker-Planck model, it assumes all collisions are soft and gradual, neglecting those hard non-differential collisions.
So it's missing a crucial aspect.
Missing a crucial aspect.
Okay, so just like the traditional Fokker-Planck model, it misses out on a crucial aspect of electron behavior.
Yeah, it misses it.
In weakly ionized plasmas.
It really does.
But the FTB model, by accounting for those hard collisions, provides a more accurate representation
Much more accurate.
of the slowing down process. Particularly at those lower energies.
Especially at low energies.
Okay, so the main takeaway from these equations and figures is that we can't ignore
we cannot ignore them.
the non-differential nature of inelastic collisions.
They're very important.
They play a significant role
They do.
in how electrons lose energy and change direction in these weakly ionized plasmas.
It changes everything.
And the traditional models that neglect this fact can lead to very misleading results.
Very misleading. And these hard collisions, what they do is they allow some electrons to maintain high energies and keep accelerating, which could significantly impact the runaway electron generation rate. And that's precisely what the researchers explored through simulations, which I think we'll get into.
In the next part.
In the next part of our deep dive.
This is getting really interesting.
It is.
I'm excited to dive into those simulation results with you.
I think you'll find them quite revealing.
Okay.
Yeah.
Okay, so we've kind of laid the groundwork here.
Yes.
Understanding why those hard non-differential collisions are so important.
They're crucial.
So let's see what happens when we actually put these ideas to the test.
Yeah, let's see what the simulations tell us.
The paper uses simulations to explore how those collisions actually impact runaway electron generation.
Right, and the results are pretty interesting.
Okay.
Yeah.
And the simulations compare predictions from the traditional Fokker-Planck model to the Fokker-Planck-Boltzmann model, or FPB model.
The FTB model, exactly.
Which we've been talking about.
Right.
Okay, so the first set of simulations focuses on something called the steady-state electron distribution function.
Yeah.
What does that mean?
So imagine you have a bunch of electrons in a plasma. They're all moving around with different energies. The electron distribution function basically tells you how many electrons have a particular energy at any given time.
So it's like a snapshot of the energy landscape of the electron.
Snapshot, yeah.
Okay.
Exactly.
And in a steady-state scenario, this distribution isn't changing over time.
It's stable.
It's reached a kind of equilibrium.
Equilibrium, yes.
Okay.
That's right.
And figure 2 in the paper shows how this steady-state electron distribution function differs between the FP and FPB models.
Yes, and it's a striking difference.
Okay.
Yeah.
So what do we see?
Well, the FPB model, which accounts for those hard collisions, right, predicts a much larger population of electrons at high energies compared to the FP model.
So those are the potential runaway electrons, ones that have gained enough energy to break free from the collisional drag force. And the FP model completely misses out on this.
It misses it completely.
Because it doesn't account for the hard collisions.
because it's ignoring those hard collisions.
Ah, that's a significant difference.
It is.
Okay.
Yeah, it's really remarkable.
So it seems like those hard collisions are really boosting the number of electrons that could potentially become runaways.
Boosting them, yeah.
And this difference becomes even more apparent
Yes.
when we look at something called the Dreiser flow.
The Dreiser flow, right.
Which essentially measures the rate at which electrons are crossing that critical momentum threshold
Yes.
and becoming runaways.
Right, so higher Dreiser flow,
Yeah.
more runaway electrons.
More runaway electrons are being generated.
Exactly.
Right.
And as you might expect,
Yeah.
the FP model, which underestimates the high-energy electron population, predicts a negligible Dreiser flow.
So very few runaways being created.
Very few, yeah.
But the FPB model tells a completely different story.
Oh, completely different.
It shows a significant Dreiser flow,
Significant, yeah.
indicating a much higher rate of runaway electron generation.
Much higher, yeah.
Okay, so the simulations are really showing us that these hard collisions can't be ignored.
They can't be ignored.
They're having a major impact on both the electron distribution
Absolutely.
and the rate at which those runaways are being generated.
Yeah, the rate is much higher.
Okay, but the researchers didn't stop there.
No, they went further.
They dug even deeper to explore how this runaway generation rate changes
Yes.
as the plasma becomes more ionized.
Right, as the ionization fraction increases.
And that's where figure 3 comes in.
Figure 3, yeah.
Right, figure 3 shows the Dreiser generation rate
Yes.
as a function of the ionization fraction,
Choi.
which basically tells us how much of the plasma is made up of free electrons versus neutral atoms.
Versus those neutral atoms, exactly.
So a low ionization fraction
Yeah.
means there are more neutral atoms around.
More neutral atoms, more collisions.
And therefore more opportunities for those hard electron-neutral collisions.
Exactly, more opportunities for those hard collisions.
Okay, and there are a few different curves in figure 3.
Yes, there are.
Can you walk us through them?
Sure, so first we have the results from the FP and FPB models,
Okay.
represented by the blue squares and the red circles, respectively. And as we've seen before,
Yeah.
the difference is quite dramatic.
Yeah.
The FPB model predicts a much higher Dreiser generation rate.
Especially at those lower ionization fractions.
Especially at low ionization fractions, yeah.
Okay, so when the plasma is less ionized,
Yes.
meaning there are more neutral atoms around,
Right.
those hard collisions have an even bigger impact on runaway generation.
Bigger impact, yeah.
Okay.
Makes sense, right.
Yeah, it makes sense.
More neutral atoms, more hard collisions.
Okay, and figure 3 also includes some theoretical predictions,
It does.
shown by the green and magenta curves.
The green and magenta curves, yes.
And those are based on analytical formulas
Analytical formulas.
for the Dreiser generation rate.
For the Dreiser generation rate, that's right.
And I see that the green curve,
Yeah.
which represents the rate when you only consider collisions between electrons,
Right, only electron collisions.
doesn't quite match up with the simulation results.
No, it doesn't.
Why is that?
Well, because it's neglecting those collisions with bound electrons in the hydrogen atoms.
Oh,
Right, so the magenta curve,
yeah.
which includes those collisions,
Okay.
provides a much better fit
To the FPB simulation,
for the FPB results,
especially at low ionization.
especially at low ionization. That's right.
So those collisions with bound electrons are playing a significant role.
A very significant role.
Okay,
Yeah,
just like we suspected.
as we thought.
So this highlights, yet again,
It does.
the importance of using a model like the FTB operator,
Yes.
which captures all the relevant collision processes.
All the relevant process.
All right, so we've seen how those hard collisions impact the electron distribution
Yeah.
and the runaway generation rate.
They have a big impact.
But how does all this play out in a real tokamak?
That's a great question.
What are the practical implications of this?
That's what we need to figure out.
Okay,
Yeah.
to answer that, the researchers went beyond these idealized simulations
They did.
and actually modeled a real tokamak startup scenario.
Level 2 tokamak startup, yeah.
And that's where things get really interesting.
Things get very interesting.
Figure 4 shows the results of this more realistic simulation.
Okay, let's look at figure 4.
There's a lot going on here, so let's break it down step by step.
Step by step.
Okay, so first
Right.
we see the runaway electron current,
The runaway current or IRE?
IRE over time.
Or time, yeah.
And as we might expect, the FPB model,
Yes.
shown by the blue solid curve,
The blue curve.
predicts a much higher runaway current
Much higher, yeah.
than the FP model, which is shown by the red dashed curve.
The red dashed curve, right?
So over time, those hard collisions lead to a much larger buildup of runaway electrons,
They do.
which translates into a higher runaway
Current.
exactly, higher current.
Okay.
Yeah.
And this difference becomes even more apparent
Even more apparent.
when we look at the runaway electron density, or NRE, in figure 4C.
NRE.
The FPB model predicts a runaway electron density that's roughly 3 times higher
3 times higher
than what the FP model predicts.
Yeah, a huge difference.
Wow, those hard collisions are really amplifying the runaway electron population.
Amplifying it, yeah.
So to understand why this is happening,
Yeah.
we need to look at the other panels in figure 4.
Okay, let's look at the other panels.
Which show how the various plasma parameters evolve over time
Right.
during the simulated startup.
During startup, yes.
So figure 4B shows the electron density and the hydrogen atom density.
Right, electron density and hydrogen density.
And I see that the electron density rises very rapidly early on.
It rises rapidly, yeah.
Eventually surpasses the hydrogen atom density.
It does.
So this means the plasma is becoming more ionized over time.
More ionized, yes.
As more hydrogen atoms are stripped of their electrons.
Stripped of their electrons, right?
The free electron density increases.
Exactly, the density goes up.
Okay.
Yeah.
And figure 4D shows the electron and ion temperatures.
Electron and ion temperatures, okay.
They're both increasing steadily as the plasma is heated.
As the plasma heats up, yeah.
Now figure 4E shows the electric field.
The electric field, right?
This is the driving force behind both the plasma heating and the runaway electron generation.
The driving force, yeah.
And I noticed that the electric field is highest early in the simulation.
Early in the simulation.
When the plasma is still relatively cool.
Cool and weakly ionized.
And weakly-ionized.
Oh, exactly.
So even though the Dreiser generation becomes less effective as the plasma heats up and becomes more ionized,
yeah.
that initial burst of runaway electrons created early on.
Thanks to those hard collisions.
Those hard collisions, right?
Has a lasting impact.
The lasting impact, yeah.
It's like a head start.
A head start for the runaway.
That the runaway electrons get.
Exactly.
And that head start can have a really significant impact.
Significant impact.
On the overall tokamak operation.
On the whole tokamak, yes.
Yeah. And the paper mentions a potential danger of a complete startup failure.
Yes.
Due to runaway current takeover.
Runaway takeover, yeah.
What does that mean?
Well, as those runaway electrons keep accelerating, they carry more and more current, right?
Right.
If this runaway current becomes too large,
Yeah.
it can overwhelm the desired plasma current,
Okay.
leading to a loss of control.
So it's dangerous.
And potentially damaging the tokamak.
Okay, and this risk is especially high?
It is.
If the electric field is higher?
Higher than in the simulation.
Than in this simulated scenario.
Right.
Yeah.
Yeah, the researchers actually ran a separate simulation with a slightly stronger electric field. And the runaway current took over completely, leading to a simulated startup failure.
So even a small increase in the electric field can have a huge impact.
Huge impact.
On the runaway electron dynamics.
On the dynamics, yeah. And it just highlights how important it is to accurately model and predict runaway electron generation.
Especially in these large-scale reactors.
Especially in ITER.
Like ITER.
Yeah. Getting this right is crucial for the success and safety.
Of future fusion power.
Future fusion.
I agree.
And you know what I think is really interesting?
What's that?
Is that this research raises some broader questions about our understanding of plasma physics in general.
Like what?
Well, if the non-differential nature of collisions is this important for the Dreiser mechanism, what other plasma phenomena might we be misinterpreting or underestimating by relying solely on these traditional models?
That neglect those hard collisions?
That ignore those hard collisions, exactly.
It's a great question.
It is.
It seems like this research has opened up a whole new avenue.
It really has.
Of exploration.
Yeah, a whole new area to explore.
And this has been incredibly insightful.
It has, I
think I need a moment to process all this.
Yeah, it's a lot to take in.
Before we wrap up.
It is.
Okay, yeah. I think I've caught my breath a little bit.
Yeah.
Those simulations were really eye-opening.
They were.
It's amazing to see how those seemingly small, hard collisions can have such a huge impact.
Huge impact.
On the overall runaway electron behavior.
On the overall behavior.
So as we wrap up our deep dive into this research, what would you say are the most important takeaways?
Well, I think one of the most important takeaways is that this research highlights the limitations of those traditional models that rely solely on the Fokker-Planck operator.
Because they don't account for those hard collisions.
Because they don't account for the hard collisions, exactly.
And as we've seen, neglecting those collisions can lead to significant underestimations of the runaway electron generation rate.
Exactly.
Especially during that critical tokamak startup phase.
That's so important.
Yeah, and we saw how those early runaway electrons generated when the plasma is most vulnerable can essentially seed a much larger runaway population.
Yes, they seed that population.
That persists even as the plasma conditions change.
It persists,
So using more accurate models, like the Fokker-Planck-Boltzmann operator, which accounts for both the soft and hard collisions.
Both types of collisions.
Is really essential.
Essential,
Now, this research focused specifically on the Dreiser mechanism, which is just one way runaway electrons can be generated.
Out of many.
Do you think these findings have broader implications for other mechanisms as well?
I do. I think it's a broader message.
Okay.
It's not just about Dreiser.
So the importance of accounting for those hard collisions.
It's about accounting for those hard collisions.
Goes beyond just the Dreiser mechanism.
It goes beyond Dreiser.
If those collisions can significantly impact the Dreiser generation rate, it stands to reason that they could play a role in other runaway electron generation mechanisms as well.
In other mechanisms as well.
So we need to revisit our understanding of those mechanisms and potentially start incorporating the effects of these hard collisions into our models.
Incorporate those hard collisions.
And it goes beyond just runaway electrons, right?
Well, it does.
I think this research highlights a broader need to carefully evaluate the assumptions underlying all of our models of plasma behavior.
Exactly. All of our models.
Especially if we move towards more powerful and complex fusion reactors like ITER.
Like ITER. Exactly.
Yeah, the stakes are getting higher.
They are.
And we need to make sure that our models are as accurate and comprehensive as possible.
Accurate and comprehensive.
We can't afford any surprises.
No surprises.
Well, this has been a truly insightful deep dive.
It has.
It's amazing how such a seemingly small detail, like those hard collisions, can completely change our understanding. To such a complex phenomenon.
How important.
Like runaway electron generation.
They really are.
And it makes you appreciate the intricacies. Of plasma physics.
Absolutely.
And it highlights the importance of continuous research and exploration. There's always more to learn and discover about these systems.
Always more.
So to everyone listening,
keep
asking those questions.
Keep asking.
Keep pushing those boundaries.
Push the boundaries.
And who knows, maybe you'll be the one to make that next big breakthrough.
Maybe we'll make the breakthrough.
Thanks for joining me on this journey of discovery.
It's been my pleasure.
I hope our listeners have gained a deeper understanding of the challenges and the opportunities. In fusion energy research.
It's an exciting field.
Okay, that's it for this week's deep dive.
Until next time.
All right, let's dive into something pretty interesting happening in the fusion world. Specifically, how those little inelastic collisions can actually make runaway electrons more likely.
Yeah, it's really turning some heads.
It seems like everyone's talking about this new research paper, Inelastic Collisions Facilitating Runaway Electron Generation in Weakly Ionized Plasmas.
A lot of the traditional assumptions about how these runaway electrons form are being challenged, especially when we're looking at tokamak startup.
And what really caught my eye is how the paper suggests that these inelastic collisions, the ones between electrons and neutral hydrogen atoms, they can actually make it easier for runaway electrons to, run away.
It's funny because you'd think collisions would slow things down, right?
Exactly. It seems counterintuitive.
For sure, but that's what's so fascinating about this research. It's like those collisions are providing a shortcut, almost like a boost, that helps those electrons reach that runaway energy level faster than we'd expect.
So, okay, let's step back for a sec. We all know runaway electrons are a big concern in tokamaks.
Oh, absolutely.
I mean, they can pick up so much energy, and if we're not careful,
they could damage the reactor walls.
Yeah, or even mess with the whole fusion process.
And as we're moving towards those larger, more powerful tokamaks,
like ITER.
Exactly, ITER, understanding and controlling these runaway electrons becomes even more crucial.
So to get everyone on the same page,
Sure.
the traditional model, the Dreiser mechanism,
Right.
that explains runaway electron formation as this kind of diffusion process, right?
Absolutely. Picture a bunch of electrons just hanging out in the plasma, each with their own energy level. The Dreiser mechanism basically says there's this constant electric field that's always trying to push those electrons towards higher and higher energies.
Like a constant force urging them to go faster and faster.
Exactly. But at the same time, they're constantly bumping into other particles, which slows them down.
So it's this constant tug of war.
That's a cosmic game of push and pull. The accelerating force of the electric field versus the slowing down effect of those collisions.
And the Dreiser mechanism says that some of those electrons manage to break free to win that tug of war by slowly diffusing across a certain momentum threshold.
It's like they finally break through a barrier, and once they do, they're off to the races, free to accelerate to those incredibly high runaway energies.
But the key assumption there, and this is where the paper really digs in,
Yeah.
is that the collisions these electrons experience are mainly small-angle collisions.
Right. Those glancing blows where they just lose a little bit of energy with each bump.
But this paper comes in and says, hold on a minute.
It's not that simple.
Especially when we're talking about those weakly ionized plasmas.
Yeah, the kind you often see during the startup phase of a tokamak. Those hard, inelastic collisions with the neutral hydrogen atoms, they can really shake things up.
So it's not just a gradual slowing down anymore.
Nope. Those electrons can lose a big chunk of their energy in a single collision. And even though that might seem like a subtle difference, it has a huge impact on how quickly those runaway electrons form.
Okay, I'm starting to see where this is going, but how do they actually prove this?
Yeah, that's a good question.
I mean, do they have experimental data to back up their claims?
Well, they rely on numerical simulations to really explore this whole thing.
Okay.
They compare two main approaches. The traditional Fokker-Planck model.
Which, if I remember correctly, focuses on those small-angle collisions.
Exactly. And then they have this more detailed model called the Fokker-Planck-Boltzmann model.
FEB.
Yeah, FPB. And that one incorporates both those small-angle collisions and the large-angle ones, including those hard inelastic collisions we've been talking about.
So it's like they're running virtual experiments, right?
Pretty much. They're trying to see how those different collision models affect the whole runaway electron formation process.
And I'm assuming they found some pretty interesting stuff.
Oh, they did. What they found was that in certain situations, especially ones relevant to tokamak startup, the model that includes those hard collisions predicts a much, much higher rate of runaway electron generation compared to the traditional model.
So those big energy jumps from those hard collisions are basically giving the electrons a faster path to becoming runaways.
Exactly. It's like they're getting a turbo boost. But to really understand how they did this, we need to get into the nitty-gritty of how they defined and quantified all these different types of collisions.
All right, let's get into it. What's next?
Well, they really get into the weeds with something called collision frequencies, which is basically a measure of how often these different types of collisions are happening. They use these symbols like E, EBS, to represent the frequency of slowing down due to soft collisions between electrons. And then there's EHD, which is for those deflections caused by collisions with hydrogen atoms.
So they're painting a picture of how often these interactions are occurring in the plasma. It's like they're building a statistical model of this whole collision process.
That's a great way to put it. And to calculate these frequencies, they don't just use simple assumptions. They use some pretty sophisticated models, like the relativistic binary encounter dipole model.
RBED.
RBD, yeah, for calculating ionization cross-sections.
Okay, I gotta admit, RBED sounds pretty intense.
It is. It basically helps them calculate the probability of an electron knocking another electron out of a hydrogen atom during a collision. You know, that process called ionization.
So it's telling us how likely it is that one of those hard collisions will actually knock an electron loose from a hydrogen atom.
Precisely. And they don't stop there. They also consider excitation collisions, where an electron bumps a hydrogen atom into a higher energy state without actually knocking an electron out. For that, they use the BE-scaled plane wave Born approximation model.
Wow, they're bringing in the heavy hitters, using all these fancy theoretical models to figure out the likelihood of each of these collisions. And all of that feeds into their overall simulation, right? The one that shows how the whole electron population changes over time.
Exactly. They combine all these microscopic details, all these individual collisions, to create a big picture of how the plasma behaves as a whole.
So, okay, they've got these detailed collision models, they're running simulations, and they're finding that these hard collisions can really boost that runaway electron generation rate. But how does all this translate to a real-world scenario? Something like ITER.
Well, that's the million-dollar question. And that's what we're going to dive into next. They took this FPB model and used it to simulate a startup scenario that's relevant to ITER. And what they found, well, let's just say it raises some eyebrows.
Okay, now you've got me hooked. Let's get into those simulations and see what kind of trouble those runaway electrons might be brewing up in ITER.
Let's do it. All right, so let's get into the real meat of this research, the math.
Okay, time to roll up our sleeves.
Exactly. Remember that kinetic equation we talked about earlier? The one that tells us how the electron population in the plasma changes over time?
Right, it's like a population census for electrons, tracking all their movements in the plasma. But I gotta be honest, that equation always looks super intimidating to me.
Yeah, it's definitely not a walk in the park, even for people who eat, sleep, and breathe plasma physics. But we can break it down. Basically, the equation says that the rate of change of the electron distribution function, which tells us how many electrons are at different energy levels, is affected by two main things: external forces, like the electric field, and then those collisions.
Okay, so we've got the electric field, kind of like a cosmic accelerator pedal, pushing those electrons towards higher energies. And then we've got the collisions that can either slow them down or, as we've been discussing, give them a boost toward those runaway energies.
Exactly. And that's where the collision terms in the kinetic equation come in. Those terms describe how interactions with other particles, both charged and neutral, affect the electron distribution.
And this is where the difference between the traditional Fokker-Planck approach and the more detailed Fokker-Planck-Boltzmann model comes in.
Right, precisely. The traditional Fokker-Planck operator assumes that collisions are mainly those small angle events, where electrons gradually lose energy bit by bit. Mathematically, this looks like a diffusion process in momentum space.
Okay, so it's like those electrons are bouncing around like pinballs, losing a little energy with each bump.
Yeah, that's a good way to visualize it. And the Fokker-Planck operator calculates the average rate at which those electrons diffuse towards higher or lower energies due to those small angle collisions.
But as we've been discussing, that's not the whole story, especially in weakly ionized plasmas where those hard collisions with the neutral hydrogen atoms can really mix things up.
Absolutely. Those hard collisions cause sudden jumps in energy, not just those gradual nudges that the Fokker-Planck model focuses on. And that's where the Fokker-Planck-Boltzmann operator, FPB for short, comes in. It includes both those small angle collisions and those high impact inelastic collisions that can transfer a lot of energy in one go.
So the FPB operator is like a souped up version of the traditional model, accounting for a wider range of collisions. But what about the math behind all of this? How do they actually represent those different collision types in their equations?
Well, they use a combination of that Fokker-Planck term for those small angle collisions and a Boltzmann collision term to capture those large angle inelastic collisions. Remember those collision frequencies we talked about earlier?
Right, those quantify how often those different types of collisions are happening. But how did they go about calculating those frequencies?
They really dug deep into the physics of electron-atom interactions. Instead of relying on simple approximations, they used really sophisticated theoretical models to figure out the probabilities of these collisions actually happening. We talked about the RBD model earlier, the one that helps them calculate the probability of an electron knocking another electron out of a hydrogen atom.
Right, that's for those ionization events.
Exactly. And then there's the BE-scaled plane wave-borne approximation for those excitation collisions, where an electron bumps a hydrogen atom into a higher energy state without knocking an electron loose.
So they're creating this incredibly detailed map of all the possible interactions between those electrons and those neutral hydrogen atoms. They're not just assuming these collisions happen, they're calculating the likelihood of each one based on the actual physics involved.
Precisely. And then they plug all of that information, all those probabilities and frequencies, into the FPB operator. That gives them a more accurate picture of how those collisions are shaping the electron distribution function.
And ultimately, that leads to a more accurate prediction of the runaway electron generation rate.
Exactly. By including those hard collisions in the model, they can see how those sudden large energy jumps give electrons a shortcut to those runaway energy levels.
Okay, I think I'm getting a better grasp on the math now.
Yeah.
But how does all of this translate to the real world? That's where those simulations come in, right?
Exactly. They took their FPB model and put it through its paces in a virtual tokamak environment.
So they built a computer model of a tokamak and then let those electrons loose to see what would happen.
You could say that. They use this software package called Hoppe, which is designed to solve those complex partial differential equations, like the kinetic equation we've been discussing.
So Hoppe is their virtual tokamak lab. They can tweak different plasma conditions, like the electric field strength and the density of neutral hydrogen atoms, and then let the simulation run to see how the electron population changes over time. And they did this with both the traditional Fokker-Planck model and the more detailed FPB model, right?
Exactly. They wanted to see how each model would affect the formation of runaway electrons.
And I'm sure the results were pretty illuminating.
Oh, they were. The simulations really brought the impact of those hard collisions to life. But before we dive into those, there's one more theoretical concept we need to touch on: the Connor-Hastie formula. Remember those curves in Figure 3 that we talked about briefly earlier?
Yeah, those analytical curves that they plotted alongside the simulation results for the Dreiser generation rate. What's the story with those?
Well, those curves represent a well-established analytical formula for calculating the Dreiser generation rate. It's been used for decades. And it's really interesting to see how the simulation results from the FPB model stack up against those predictions.
Do they line up?
Not exactly. The FTB model actually predicts lower Dreiser generation rates compared to the Connor-Hastie formula. However, they're still much higher than the predictions from the traditional Fokker-Planck model.
So it's like the FPB model is finding a middle ground. The traditional approach underestimates those runaway electrons, while the Connor-Hastie formula might be overestimating them.
That's a good way to look at it. It shows that there's still a lot of discussion and refinement going on with these models. But even though it doesn't perfectly match the Connor-Hastie formula, the FPB model is still revealing something crucial: the significant role those hard collisions play in boosting the runaway electron generation rate, something the traditional approach missed.
So it's adding another layer of complexity to our understanding. Those hard collisions are important, even if their impact isn't as extreme as some analytical formulas might suggest.
Right. And with that in mind, we're ready to really get into those simulations of an ITER-relevant startup scenario. Let's see how those runaway electrons behave in our simulated fusion reactor.
Let's fire up the simulation and see what kind of havoc those runaway electrons might unleash in ITER. All right, we've covered a lot of ground here. We've talked about the theory, the math, and the simulations, but now the big question: how does all this stuff about inelastic collisions and runaway electrons play out in the real world, especially for ITER, that huge project trying to make fusion power happen?
Well, it's a question that keeps a lot of fusion researchers up at night.
I bet.
And this paper gives us some pretty important, if not slightly worrying, insights. They took that fancy Fokker-Planck-Boltzmann model, the one that factors in those hard collisions,
Right.
and used it to simulate what happens during the startup of a tokamak like ITER.
Before we jump into those results, can you remind me why that startup phase is so crucial? What makes it so tricky to get a tokamak up and running?
Sure. During startup, the plasma is still pretty cool and not completely ionized. It's a bit like trying to start a massive engine in the dead of winter.
Oh, I see.
It takes time, a lot of care to get everything working smoothly.
And those runaway electrons are like wrenches being thrown into the engine, right?
That's a great way to put it. They can really mess things up and potentially cause damage.
Right.
So during startup, we depend a lot on what we call ohmic heating to get the plasma temperature up.
Basically, the electrical resistance in the plasma generates heat.
Exactly. Think about those old-fashioned incandescent light bulbs. The filament heats up and glows because of electrical resistance.
Makes sense.
But here's the issue. If too much of that current is carried by runaway electrons, which are basically off doing their own thing, separate from the main plasma,
Right.
ohmic heating becomes way less effective.
It's like trying to heat a house with faulty wiring. The current's flowing, but it's not going where it needs to actually warm things up.
Precisely. And that can cause a whole cascade of problems. The plasma might not get hot enough for fusion, and the whole discharge could become unstable, leading to, you guessed it, disruptions.
And disruptions are bad news.
Yeah.
Right? That's when we lose control of the plasma, potentially damaging the tokamak and halting the experiment.
Exactly. Disruptions are a major headache in tokamak research, and these simulations are suggesting that those hard, inelastic collisions, the ones that can send those electrons toward runaway energies, can actually make this problem worse, especially during startup.
Okay, enough build-up. What did those simulations show? How bad is this runaway electron situation in their ITER scenario?
Well, the results are pretty striking. They show that when you factor in those hard collisions, you end up with a much higher final runaway electron density and current compared to the traditional Fokker-Planck model simulations, which don't completely account for those big jumps in energy.
So it's not just theoretical, it's a real difference that could have serious consequences for ITER.
Definitely. And remember, ITER is designed to operate at much higher power levels than any other tokamak we've built.
Right.
So if there are more runaway electrons than we thought, there's a much greater risk of damage and those dreaded disruptions.
Let's get into those simulations. They zeroed in on the startup phase of an ITER discharge, right?
Mm-hmm.
What exactly were they tracking in their virtual tokamak?
They looked at a bunch of different plasma parameters over time, things like the runaway electron current and density, the total plasma current, the densities of electrons and hydrogen atoms, and even the electron and ion temperatures. They basically monitored everything as the plasma went through that startup process.
And I assume they compared the results from those traditional Fokker-Planck simulations to the results from their more detailed FPB model, right? The one with those hard collisions.
That's right. The goal was to see how those different collision models would change the way those key plasma parameters evolved, especially the runaway electron behavior.
And given all the attention those hard collisions got in the paper, I'm guessing those differences were pretty significant.
You bet. The simulation showed those runaway electrons building up much quicker in the FTB model, particularly in the early stages of startup. It's like those hard collisions were giving the electrons a superhighway to runaway energies.
Okay, let's take a look at figure 4. It seems to be the heart of this analysis. It shows those different plasma parameters over time during the simulation. What jumps out at you when you look at this figure?
The most noticeable thing is how different those curves are. The ones from the traditional Fokker-Planck model versus the ones from the FPB model.
Right, right.
When you look at the panels showing runaway electron current and density, the curves from the FPB model are way higher, especially at the beginning of the startup.
Yeah, those curves are shooting straight up. It really shows you how much faster those runaway electrons accumulate when you take those hard collisions into account. It's a clear visual of how much those seemingly small events can impact the overall plasma.
You got it. And this runaway electron buildup has a ripple effect on other parameters too. Like, you'll see that the total plasma current is affected because those runaway electrons start taking over the current flow.
Which messes with the ohmic heating, right?
Exactly. We need that current to be flowing through the main plasma to raise the temperature properly.
And those runaway electrons are basically stealing energy that should be going towards heating the whole plasma.
Right on. So we have runaway electrons building up, potentially disrupting the heating and increasing the risk of disruptions. But the paper takes it even further, right? They actually simulate what happens when those runaway electrons take over completely.
Yeah, they call it a runaway current takeover. Sounds like a worst-case scenario for ITER.
It pretty much is. It's when the current carried by runaway electrons gets so big that it becomes the dominant current in the plasma, basically hijacking the whole discharge.
And this isn't just a theory. They saw this happening in their simulations, right?
Oh, they did. And what's even more concerning is that it didn't take some crazy, unrealistic conditions to trigger it. Even a small bump in the electric field strength could cause this runaway current takeover, basically preventing the tokamak from starting up properly.
That's a bit unnerving. Those runaway electrons, boosted by those hard collisions, pose a real threat to ITER, but I'm sure the ITER team has some plans to deal with them, right?
Absolutely. Mitigating runaway electrons is a top priority for the fusion community. ITER researchers are looking at all sorts of strategies.
Like what?
One approach is to use carefully designed magnetic fields to control the plasma and make it harder for runaway electrons to form in the first place.
So it's like building magnetic fences to keep those runaway electrons in check.
That's a good way to think about it. Another strategy is to inject impurities into the plasma, which can make electrons collide more often and make it tougher for them to accelerate to those runaway speeds.
Like putting obstacles in their way, slowing them down.
Exactly. And they're also looking at using radio frequency waves to interact with the runaway electrons, either to slow them down or kick them out of the plasma entirely. It's a multi-pronged approach because it's likely going to take a combination of techniques to really control these rogue particles in ITER.
That's like a high-stakes chess match, trying to outmaneuver those runaway electrons and ensure that this ambitious project succeeds. But it sounds like there are a lot of smart people working on this. That's got to be encouraging.
For sure. Runaway electrons are a huge challenge, but not an impossible one. The research we talked about today is a big step forward. It gives us important clues about how runaway electron generation can be amplified.
And it shows how important it is to pay attention to those seemingly small details, like those hard collisions that might have been overlooked before.
Absolutely. Fusion energy research is a journey of constant exploration and discovery. This paper shows us that even tiny details can unlock big breakthroughs and help us overcome the challenges ahead.
Well, I'd say we've done a pretty thorough job exploring the world of runaway electrons and the surprising influence of those hard collisions. We've talked about the theory, the math, the simulations, and what it all means for ITER. It's been a really fascinating deep dive. I think we've all learned a lot more about the complexities of plasma physics.
I agree. And I hope this deep dive has made our listeners curious to learn even more about this exciting field and the ongoing quest to make fusion energy a reality.
That's all for today's deep dive. Thanks for joining us on this journey into cutting-edge fusion research. Until next time, keep those electrons in check and your curiosity burning bright. Welcome to another deep dive. Today we're looking at this paper all about the role of inelastic collisions in the generation of runaway electrons in plasmas.
Yeah, it's a pretty interesting one.
And, maybe someone listening is thinking like, wait, why are we talking about runaway electrons? Well, what's the big deal?
Well, if you're trying to contain a super hot, electrically charged gas, and suddenly some of those electrons decide to start zooming around at close to the speed of light.
Yeah, it's probably not good.
Not ideal.
No.
Not at all. Especially when you're trying to create, a nice, stable, controlled fusion reaction like they're doing at ITER.
Right. And that's, part of what makes this paper so interesting is they're really focusing on these early stages of a tokamak startup when the plasma is, it's not fully ionized yet. And it turns out that can really change how these runaway electrons behave.
Yeah, that's right. The usual models we use to predict runaway electron generation, they kind of assume that the plasma is fully ionized, and that might not be telling the whole story when you're dealing with these weakly ionized plasmas.
So let's back up for a second and talk about the classic way of understanding runaway electron generation, which is the Dreiser mechanism. Can you give us a quick refresher on that?
Sure. So the Dreiser mechanism basically describes how electrons in a plasma, under the influence of an electric field, can gain enough energy to overcome what we call a critical momentum threshold.
Okay.
And once they cross that threshold, they're basically free to accelerate to super high energies and become runaway electrons. And the way we traditionally model this process is using something called the Fokker-Planck equation.
Right.
But the Fokker-Planck equation, it really focuses on these small angle collisions between electrons and ions, where the electrons kind of gradually diffuse to higher energies.
Okay.
And what this paper is arguing is that in these weakly ionized plasmas, that approach might not be accurate enough. Because there are also these inelastic collisions happening where an electron can lose a large amount of its energy all at once, and the Fokker-Planck model doesn't really capture that very well.
So these inelastic collisions, they're kind of like a hidden energy drain that we haven't been fully accounting for.
Exactly. And the paper argues that they can be a big deal, especially in these weakly ionized plasmas, where the critical momentum threshold for runaway electron generation is lower.
Interesting. So it's like the bar for becoming a runaway electron is lower in these weakly ionized plasmas, and these inelastic collisions can really knock the electrons back down before they even get a chance to run away.
Right. It's like they're trying to climb a hill, and these inelastic collisions are these gusts of wind that keep pushing them back down.
That's a good analogy, Sue.
Yeah.
So this is all very interesting from a theoretical perspective, but how does it actually play out in the real world? I mean, what are the practical implications of this for something like ITER?
Well, ITER is designed to operate with a weakly ionized plasma during its startup phase. So if this paper is right and these inelastic collisions are playing a bigger role than we thought, then we might be underestimating the risk of runaway electron generation during those early stages.
And that could be a problem.
It could be a big problem. Remember, runaway electrons can carry a lot of energy, and if they hit the walls of the tokamak, they can cause serious damage.
So we're not just talking about some theoretical curiosity here. We're talking about something that could potentially impact the success of a multi-billion-dollar experiment.
Exactly. This paper is basically a wake-up call saying, hey, we need to take these inelastic collisions seriously if we want to make fusion energy a reality.
So what do we do about it? Is there a way to account for these inelastic collisions in our models and make more accurate predictions?
That's what the authors of this paper set out to do. They propose using a new type of operator called the Fokker-Planck-Boltzmann operator, or FPB for short.
Okay, the Fokker-Planck-Boltzmann operator.
Yeah, it's basically a hybrid approach that combines the traditional Fokker-Planck model with another model called the Boltzmann operator, which is better at handling those large energy transfer collisions.
So it's like taking the best of both worlds.
Right. And they use this new FPB operator to run some numerical simulations and compare the results to the standard Fokker-Planck model.
Ooh.
And let me tell you, the results are pretty striking.
Okay, let's dive into those results and see what they tell us.
All right, let's do it. All right, so to really understand what they did, we need to take a look at the math they used. And the heart of their model is the kinetic equation for electrons, which describes how the distribution of electrons in the plasma evolves over time.
Okay.
And the equation they present is Phet plus 8 plus A8 plus CEI phi plus CEH phi.
Okay, so that's a lot to unpack. Can you break it down for us? What are all those symbols?
Sure. So Phet, that represents the electron distribution function, which is basically a way of describing how many electrons you have at a particular momentum and pitch angle.
Pitch angle.
Yeah, so the pitch angle is basically the angle between the electron's velocity and the magnetic field.
Got it.
So Phet tells you how many electrons are moving in a certain direction with a certain speed. And then the left-hand side of the equation that describes how this distribution function changes over time due to the electric field.
So that's the part that's driving the electrons to become runaways.
Exactly. And then on the right-hand side, we have the terms that represent the effects of collisions. There's CEI phi, which accounts for collisions between electrons and ions. And then there's CEHE, which describes collisions between electrons and neutral hydrogen atoms.
Okay. And that's where those inelastic collisions come in.
Exactly. And this is where the authors introduce their Fokker-Planck-Boltzmann, or FPB operator. They break down this electron-hydrogen collision term, CEA phi, into two parts.
Okay.
So they have C8A phi, CHHFKE plus BHA phi.
And each of those represents a different type of collision.
Right. So CEHFPA phi, that's the Fokker-Planck operator, which is good at describing those small angle collisions we talked about earlier.
Yeah.
And then BHFE, that's the Boltzmann operator, which is better at modeling those large energy transfer inelastic collisions.
Okay. So they're basically using two different tools to handle different types of collisions.
Exactly. And to distinguish between those two types, they use this thing called the soft-Ard separation factor, which is denoted by H.
Okay. And what does that do?
Well, it basically sets a threshold for how much energy an electron can lose in a collision. If the energy loss is above this threshold, then it's considered a hard collision, and it's handled by the Boltzmann operator.
And if it's below the threshold?
Then it's a soft collision, and it's handled by the Fokker-Planck operator.
Okay, so it's like a filter that separates the big hits from the little nudges.
Exactly. And this is really important because those big hits, those inelastic collisions, can have a much bigger impact on the electron's energy than those small angle collisions.
Right, so they've got this new FPB operator that can handle both types of collisions. But how do they actually apply it to these specific types of inelastic collisions?
So they define the Boltzmann operator specifically for ionization and excitation. So for ionization, they use BH is SAFE, which is given by this equation. BH is BHMZ PP S2P 1 2 1 H 12 H NFTP 1 2 12 H 1 1 plus 0.1 P plus 12 P1 with PP 1 1 1. Okay.
Okay, so what does all that mean?
So this equation describes how the electron distribution function changes due to ionization collisions, and it takes into account all the possible momenta and pitch angles of the incoming electron that could lead to ionization.
Okay.
So there are a lot of variables in there, but one of the key ones is delta dW, which is the differential cross-section for ionization.
And what does that tell us?
It basically tells you the probability that an electron with a certain energy will ionize a hydrogen atom and produce a secondary electron with a certain energy.
Okay.
And then there's He-hardest Phet, which represents the loss of electrons from the distribution function due to these hard ionization collisions.
Okay. So this equation is basically accounting for all the electrons that are lost due to ionization.
Exactly. Now for excitation, they use a similar approach with a Boltzmann operator, denoted by BHXSAE. But the equation is a little different because the physics of excitation is a bit different from ionization. So the equation they use is BHAFE plus E1H, E1T plus ENX, P plus 1N, S0E, P plus 1H, E1E, okay.
Okay, I'm seeing a lot of new symbols here. Can you break this one down too?
Sure. So this equation basically sums up the contributions from excitations to different energy levels within the atom, and each term in the sum represents a different energy level.
Got it.
And one of the key variables here is Inex, which is the rate of excitation from the ground state to the nth energy level.
Okay.
And then E1N is the energy difference between those two levels.
So it's the amount of energy required to excite the electron to that level.
Exactly.
Yeah.
And then you'll also notice these heavy-side step functions in the equation, which are denoted by H.
Yeah, what do those do?
Well, they basically act like a switch. They make sure that only the contributions from excitations that have enough energy to actually occur are counted.
Okay, so they're like a quality control mechanism.
Yeah, you could say that. So they've meticulously defined this FPB operator, and they've carefully crafted the Boltzmann operators for ionization and excitation, and now they're ready to put it all together and see what happens.
So they plug this new FPB operator into their simulations, and what do they find?
Well, they find that when they take these inelastic collisions into account, the runaway generation rate can be significantly higher than what the traditional Fokker-Planck model predicts.
And this is especially true during that early startup phase when the plasma is weakly ionized.
Exactly, because that's when those inelastic collisions are most important.
So it's like we've been missing a big piece of the puzzle all along.
Yeah, and this has some pretty serious implications for ITER and other fusion experiments because it means that we might be underestimating the risk of runaway electrons during those critical early stages.
So what can we do about it?
Well, that's a question for the next part of our deep dive.
Okay, so we've really spent some time digging into the math behind this new Fokker-Planck-Boltzmann operator and how it takes into account those inelastic collisions.
Right, and we saw how those simulations show just how big of an impact they can have, especially during those first stages of a tokamak startup when the plasma isn't fully ionized yet.
Exactly. So now let's talk about what all of this means for actual fusion experiments. Like, what does this new understanding of inelastic collisions mean for ITER?
Well, you know, the big takeaway here is that if this FPB model is right, and these inelastic collisions really are as important as this paper suggests, then we really need to think carefully about how we handle runaway electrons in these big tokamaks.
Especially during that early startup phase when the plasma is still weakly ionized.
Exactly. And you know, those simulations we talked about earlier of ITER's startup, the ones where the runaway current could potentially take over completely, those were done using this new FPB model, and they paint a pretty concerning picture of what could happen if we don't properly account for these inelastic collisions.
It's like we've been underestimating how dangerous they can be.
Yeah, kind of. Like we've been trying to navigate a minefield with a map that's missing a bunch of mines.
So what can we actually do about it? I mean, is this a deal breaker for ITER?
No, not necessarily. I mean, the good news is now that we're aware of this potential problem, we can start figuring out ways to address it.
Like what? What kind of solutions are we talking about?
Well, one approach could be to find ways to speed up the ionization process during that initial startup phase.
So get the plasma fully ionized faster.
Exactly. If we can shorten the amount of time that the plasma spends in that weakly ionized state, then we can reduce the window of opportunity for these inelastic collisions to cause problems.
Makes sense. So it's like we're trying to race through that danger zone as quickly as possible.
Right. And another thing we could do is look at ways to carefully control the electric field in the tokamak. The idea is to try and limit the number of electrons that get pushed over that critical momentum threshold in the first place.
So it's all about fine-tuning the controls to keep the runaway electrons in check.
Exactly. It's a delicate balancing act. But the point is that now that we know about this potential issue, we can start looking for solutions.
This all seems very complex. It sounds like there's still so much we don't know about runaway electrons and how to control them.
Oh, absolutely.
Yeah, this is a very active area of research, and there are a lot of brilliant people working on this problem. But, you know, that's what makes it so exciting.
Right.
There's always something new to discover.
It's true. It's like we're explorers charting a new frontier. And every new discovery, even one that might seem like a setback at first, can ultimately help us get closer to our goal.
That's a great way to put it. And I think this paper is a perfect example of that. It's a reminder that even the most subtle processes can have a huge impact, and that we need to be constantly questioning our assumptions and refining our models if we want to make fusion energy a reality.
It's a humbling thought, but also an inspiring one. It shows just how much potential there is for innovation and discovery in this field.
I agree. And on that note, I think we've reached the end of our deep dive. I hope you found this exploration as fascinating as I did. I certainly did. It's been a real eye-opener. And for our listeners out there, if you want to learn more about this topic, we encourage you to check out the paper we've been discussing. It's a really thought-provoking read. And as always, Keep exploring, keep asking questions, and keep those minds engaged.